need to take a chunk of water out of all the water that is touching the skate. So we're going to make a free body diagram of this little chunk of water. So we're going to try for some class involvement, and if any of you guys can say in the chat what forces are going to be acting on this water, that'd be awesome. We're really proud of you. Oh my gosh, that was amazing. Weight of the water is going to be acting down. Weight is also going to be there. That was just so fantastic. Oh yay, horizontal pressure. So this is going to be the force in the water. There's no water below the gate, so we don't have to care about the vertical force. And then we're going to have to there's all these forces coming off the gate onto the water. So we're going to have to look at force horizontal, and then force vertical are the forces from the gate acting on the water. The problem is that this free body diagram doesn't have P in it, and P is all we care about. So we have to make two free body diagrams. And this one's going to have P in it, and then it's going to have the opposites of like the reactionary forces of FH and FV that are completely equal but working in the opposite direction. And then we have the hinge, which is going to have the hinge Y, and then hinge X forces. So the forces that the hinge is providing in the X and Y direction. And then of course we need our axes. Okay, cool. So we have our free body diagram. So I'm going to look at this and I'm going to say, what are all my unknowns? Okay, I don't know this, I don't know this. This is the same thing, but I still don't know it. I don't know this, I don't know this, I don't know this. I can solve for this and this. So I'm freaking out because I have a million unknowns, but there are some things I can solve. So I'm going to start with this free body right here. So all the forces in the X. Simple at first. So we can see that force from the water is acting positively, and that's minus force horizontal from the dam. And that equals 0. And then all the forces on the Y. So that's going to be force vertical acting positive, and then minus weight acting negative equals 0. So now at this point, I could keep on making equations because I obviously don't have enough equations for all my unknowns, but I'm going to solve for some of these unknowns just to make myself less overwhelmed. So the first one we can solve for is force. Oh, it's not. Silly. So force water. So we are going to look on page 18 of your notes, and it's going to be a very familiar equation, which is gamma water HC times area. Gamma water we know, which is 62.4, if we're doing that, yeah, pounds per force per foot to the third. HC is, it's just going to be half of this, so the centroid of the thing. And one thing that's really helpful is if you're picturing that you are force water and you are looking at this little segment of water, all you see is a rectangle. You don't know that there's a curve on the back side of it. I don't know what you guys can see. So all I see is a rectangle in front of me. I care about the centroid of that rectangle, so that's just going to be 6 divided by 2 feet. And then the area of that rectangle, I don't realize that there is a half or a quarter circle on the other side. So it's going to be 6 feet, and y'all can let me know if that doesn't make any sense at all, times the width, which is 20 feet. And then I make sure that that was all right. We could plug it into the calculator. Times 3 times 6 times 20. Okay, so I'm going to get 22,464 pounds. Oh my gosh. And also I can X out all these units. So I have pounds. And I'm going to keep it without simplifying my sig figs yet, because that might mess me up if I simplify too soon. So this will tell us that FH equals 22.464 pounds. Okay, next we have weight. That's going to be page 1 of our notes. So we're pros at this by now. So that's gamma H2O times the volume of this little quarter circle thing. Gamma H2O, you guys have memorized because you're engineers. I don't have that memorized. And then volume of the quarter circle. We have the diameter, so I'm going to do pi over 4 times 6 squared times, I hope I'm doing this right, times 20 feet, because that's the width. So that's my volume. and I don't have any units. Now I do. Okay, and if I did all that on my calculator, times 5 divided by 4 times 6 squared times 20. It's mad at me. We did it wrong. Times 4 times 5 divided by 4 times 6 squared times 20. Okay, I get 35,286 pounds. Very uglily written. So all I have is pounds left. Okay, so now we know FB equals 35,286 pounds. Any questions so far? We'll be doing a clicker question today. Ryan, you're not allowed to leave this class because of clicker questions, but so I'm not going to answer that question. Okay.
I'm Ella.
So now we go to the next section. The fluid sphere is already here, so she wrote out our free body diagrams again. And I'm just taking over the information we already got and put it over on this slide.
Emma?
Yeah.
Could you go back one?
Yeah. Is my handwriting
in the W equation, what is the V with the dash through it?
That's volume.
Okay.
So on your first page of the notes, I think you have that gamma equals weight over volume. So I just rearranged that. And I think they write it this way, engineering things do, because they're afraid you're going to think it's velocity. Hopefully the V with the slash isn't velocity. Okay. Any other questions? Cool. Okay, so let's see what we know and what we don't know. So now we know this. Hopefully everything's okay. We know this, we know this, we know this, we know this, we know this. We don't know that, we don't know that, we don't know that. Okay, so I have to move over to this scarier free body diagram. I could do all the forces in the y, all the forces in the x in a moment, and then I could get 3 equations and I have 3 unknowns, which is awesome. However, I remember statics. I'm incredibly smart. So I'm going to do a moment around this spot right here, which I'm going to name O, so that I don't ever have to solve for hx and hy, because I don't care about them. They're not in the problem statement. That sounds difficult. So in order to do a moment about O, I need to find the distance from these forces to O. So I'm going to have to figure out this, which is going to be called LP. I'm going to have to figure out this, which is LY. And I'm going to have to, that's not right at all. That is going to be called LV, because it's a different distance from here to here, which is a little hard to see. And then, oh my gosh, I'm getting confused from my own diagram. And then this is right? LH. So that's distance from F horizontal to O. Okay, so all the moments around O, we're going to do our little right-hand rule, and we're going to know that this is positive. So all the moments around O, let's start with P. So P is going to be pushing it in the positive direction. So P times LP. And then FV will be pushing it in the kind of right. So it's negative. It's pushing in the wrong direction, I guess, the negative direction. And that's going to be times LV. And then F horizontal will also be doing the same thing. And it's going to be multiplied by LH. It's also pushing it negative. And that's all equal to 0. Okay, what do we solve for? LP is the easiest thing to solve for. So we do it first. And that is literally just this distance. So it's 6 feet. We did it. Yay. Okay, P we don't know. FV we have LV. Which one is LV? Okay, so we have to think back. It's a little weird, but all forces from the water acting perfectly like vertically are going to be just working on the centroid. So like if we had a box and we also had water pressure, the force from water pressure working up or down, it's just going to be working on the centroid. Hopefully I'm right. So you guys are you know where all your tools are. You're going to Google it. And you're going to get something like this, which is like you're going to Google centroid of a quarter circle. And what are you going to get? You're going to see that the centroid is at 4r over 3 pi. So in this direction and this direction, it's in 4r over 3 pi. Luckily, this distance is actually LV. It's just hard to tell. So that's exactly what we're looking for. I feel like there'll be questions about that because I did it confusingly.
And just to interrupt there for a second, you can also, on page 16 of the notes, they have the centroid and stuff, so you can also, there as a reference if you don't want to.
Oh, awesome.
That's fine as well.
Yeah, that'd be better to use your notes. Okay, so 4 and then 6 over 3 pi, which is going to be something like, it's going to be 8 over pi. We'll just keep it like that. And then finally, we have LH, which, okay, so once again, we have to remember that like FW, FH is just looking at the dam like this. All it sees is a rectangle. It doesn't realize that the dam is curved coming towards it. It has no depth perception. So we're going to, we got to find our YRs, which is going to be on page, I think it's page 20. We figure out how to solve for this value. And because what we actually care about is this value, this is LH, we're going to have to do 6 minus this value. So we care about this, we know how to solve for this. So we're going to have to do 6 minus, and in the notes, I think they call it YR, hopefully. Yeah, it's called YR. Okay, so this is going to end up being 6 minus YC plus IXC over YCA. This is from your notes, and it's page 16, actually. Nope. Okay, it's all over there. I think it's page 20. Maybe Alexi will put it in the chat what page it actually is on.
It's page 20.
Nice. Okay, and then we have to find this guy, which is some other page in your notes, now that I'm all mixed up. Oh, here it is, page 16. You're going to see that there's no quarter circle thing, but there is that rectangle, which is exactly what we want, because all this guy can see is a rectangle. And we're going to choose, and we're going to have it rotating like this way. You can see what I'm doing. So this guy is going to be 1/12. That got weird. Okay. 1/12 BA cubed, which equals 1/12, I think 26 cubed. Okay. So this equals 6 minus YC, which we found earlier. It's just the centroid of the rectangle as it sees. So it's going to be 6 over 2. Feet, I lost all my units. Whoops. Plus 1/12, 20 feet, 6 cubed feet cubed over YC again, which is 6 over 2 feet, times area, which is 20 feet, times 6 feet. So you're going to do all that. I'm running out of time, but I think you literally get like 2 feet. If you're super smart, you would also know that you could have just done 6 feet over 3, because that's a pattern we found earlier. But we don't want to do that. It's always going to act like 2/3 down, or a lot of times it will act right.
It'll always act 2/3 down if it's at the surface, right? If this is just like, if we drew our prism, our triangle out, it's going to act 2/3 of the way down.
Now my pen's not working. Okay, well, now I don't know how to erase, but that's typical. Okay, so we have run out of time, but we know this, 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 we know this. Oh wait, we don't know this. So you're going to put it all, the whole equation in terms of P, and then you're going to divide by LP, if that makes sense. It's going to be P equals FV. Oh, that's not V, is it? Yeah, it is. V plus FH LH over LP. Plug in all your unknowns. But I was too slow, so we're not actually going to find the numbers. Any questions?
So I have one quick question. If we were to do this like on an exam, to find like LP, would we need to do like the whole math, or can we just like state like if we know that it would act 2/3 of the way down?
For LV?
Yeah.
Oh no, LH.
Oh, I'm sorry.
Yeah, you could say it acts 2/3 of the way down, I'm sure. Yeah.
Okay.
Just like, and if you want to be safe, just put like a little, like, I know this will act this way. Yeah.
Cool. Thank you.
Awesome. Now Alexis can go.
And just one thing while we're still talking about that problem, when you're doing your Wiley problems, you're going to go through that problem, and obviously, you're going to calculate all the numbers. It's going to ask you to put in like boxes of equations, and some people came into office hours and it was kind of finicky. So I guess I'll give advice. So when you have a gamma, you don't need to say it's gamma water, just say it's gamma when you're writing those equations. And whenever you have like the length 6 feet of the, right, that's like the radius of this quarter circle, use H, because it's the same thing as the depth H. So it doesn't seem to like R, it seems to like H. So if you have trouble with that, you can come into office hours later as well. But that's just some advice when you're doing that, writing the actual equations in the boxes for that problem. All right, so is there another comment? Oh, someone's asking, what did we get for P? We're not going to tell you. You're going to have to find that out. But these should be all the steps for you to get that. So, all right, cool. I'm going to do, it's not a homework problem, but it's pretty similar to some of the other homework problems. So let me just share the PowerPoint. All right. Looks like it's struggling. Oh, here we go. Oh, I went to the beginning. Okay. Oh, the writing's not there anymore. Whoops, there's my... Okay, so in this example, we have kind of pretty similar. We have, again, this weird quarter circle shape, and we're going to determine the horizontal and vertical components of the force of the water on a 6-foot section length of the curved section AB, which has a width of 1 foot. So I'm just grab my notes here. Okay, so we're asking about this, like, ooh, I gotta get my pen working. Oops. There we go. Okay, so we're this kind of section of the wall, like this is what we're looking at. We want the force, how is it phrased? We want the horizontal and vertical components of the force of the water on this section of the wall. So like before, first step is going to be to draw a free body diagram. So we're going to draw a free body diagram that includes this chunk of water, and like not the wall on the side, and just the water in here. So it's just this big semicircular chunk of water. So we're going to draw it over here. And I can't really draw straight lines very well, but that's okay. So it's this, I keep saying semicircle, but it's really a quarter circle, and I think you guys called that. All right, so like the problem before, can some people tell me what are going to be the forces acting onto this shape? Can you say in the chat? And I actually can't see the chat, so can you tell me, Emma, if they say something?
It's great right now. Oh, vertical force of water? Yep.
So we're going to have that vertical force of water. Now, so that one's kind of, you have to think about it a little bit. So there's going to be a vertical, like the water, there's going to be water pressure like pushing down on the bottom here. But we drew it, so when you draw a free body diagram, you want the forces that act on your free body diagram. So there's going to be a force, a normal force opposing that vertical water pressure. So that's the pressure, that's the force that we're going to use on a free body diagram. So we're going to call that F2. But those two forces are going to be equal to each other. So we're going to calculate the water pressure times the area, but it's really, we're in our free body diagram, we're actually having a force that goes up. All right, what other forces are there?
Okay, there's someone said horizontal force.
Okay, yep, there's going to be a horizontal force on the water, like this pressure pushing on the pressure over here, pushing on the water inside our little free body diagram. So that force is going to act somewhere down at towards the bottom. We'll call that F1. All right. Now there's a couple more forces.
Someone said weight question mark. Oh, now we have some more confident weights.
Okay, cool. Well, we have a weight, and it's going to act down. And remember, these forces are all going to act in certain directions that may or may not be important later. But when we draw our free body diagram, we don't need those exact dimensions. So yeah, we have weight. All right, and I'll say the last two, right? The last two is we want the horizontal and the vertical components of the force acting on this. So those are just going to be acting like from this wall onto the surface. So we're going to have a force horizontal and a force vertical. And these are the two things that we want. So as Emma was going through, we don't know this, but we can find this, this, and this. We can find F2, F1, and W. We just have to go and figure those out. Okay, so first, yep. And then I'm gonna actually go to the next page because I have the free body diagram written a lot better. So it's nice and neat. So we're gonna go to the next page. Why isn't it there? There we go. Okay, so we have same free body diagram that I drew, just a little bit neater. The volume, again, they have this V with a slash, which means volume of the water inside that section. So first we're gonna do...
Alexi?
Yeah, go ahead.
So F2 is the normal force in response to the weight of the water, right?
Yes, yeah.
So is F1 then the force of the water onto the gate?
F1 is the force of, remember there's no gate here, F1 is the force of like this water pushing on this water.
So wouldn't there also be a vertical force on top of the normal force of the water that's pushing against the top?
Say again?
So, I mean, F2 comes from it's a responsive force from the weight, right?
Yep.
Then you have F1, that's a force onto the circular part just from the water. Wouldn't there also be a vertical force from the water onto or I guess it'd be from the bottom.
Yeah, remember, we're just looking at this chunk, right? So there's no force that acts on, there's no force acting like here or something. Like, there is, but we've simplified it to just have forces acting only on the sides of this free body diagram, only on the edges of it, except the weight that's acting internally from it. Does that make sense?
I guess what I'm asking is, why is there a force of the weight or of the water horizontally, but there's no force from the water vertically, besides its weight? Or is that the force?
So so you mean like there's no vertical force of the water coming down here? Is that what you mean?
Yeah.
So remember, there's no water above there. That's the, no. That's the wrong way to put it. So, right, the water indeed is pushing up, the water is pushing up here against this surface, but that force is being opposed by this FH and F vertical, which is what we're trying to find out. So we want to look at all the forces on the outside of this free body diagram. We have force 1 that's pushing in horizontally from the side. We have F2 that's pushing vertically up, and then we have force horizontal that's pushing to the sideways, and force vertical that's pushing down on this side of the surface. So, that force of the water, that force exists, the force of the water pushing this way, but that's going to be incorporated in our FH and our FV, if that makes sense.
Okay, I see.
Yeah, okay. So it's it's important to think about where you draw your free body diagram is really important, because that affects where these kind of forces are, right? There's other forces that aren't used because of how we drew the free body diagram. All right, so I'm going to continue on. First we're going to calculate F1. So force 1, F1 is the force on the side. So like we've been doing a lot before, the force 1 is going to be gamma times HC, we'll call this HC1, and times the area. So, right, this is a pressure, and this is times an area, and we get a force. So we know gamma is going to be gamma water, so that's pretty simple. And what are we are in imperial, so it's going to be 62.4 pounds per feet cubed. And then HC is the depth to the centroid. So remember, when we calculate the force, we want the average force. So there's kind of a triangle, there's a trapezoid of force along on this side, but we just want to know what the average force is, and that average is going to be right at the middle. So that's not exactly where the force acts, but it's going to be how we calculate it. We say it's the force at the centroid is the average force, and we multiply the average force by the total area. So that HC1 is going to be, first we'll go 15 feet down, or I guess in my example it's 12 feet. Do I have a different, yeah, sorry. So this is 12 feet. No, sorry. This is 6, oh yeah, it is 12, I don't know why. Yeah, 12 feet, and then we're going to go halfway down here. That's 3 feet, half of 6 feet. So it'll be, 12 feet plus 3 feet equals 15 feet. It's kind of hard to see, but I think you guys can get that. So we have 15 feet. Now the area is just 6 feet tall, right? And the width is 1 foot. So 1.0 feet. Sorry, the writing's kind of on the edge of my computer here. Now we're going to cross our units out. We got a foot, multiply and cross out with those feet cubed. And we get, if we do the math, we get F1 equals 5,620 pounds. Okay, so what are we going to do with that F1? So I should have done this before, but we can do the step now. We're going to have we want to find the equations, like we want to do the sum of forces on this shape. So we could also do a sum of moments, but we don't really have anything turning, and so we might have to do that, but first we'll start with just the sum of forces in the x and the sum of forces in the y direction. So if we go the sum of forces in the x direction is going to equal 0, right? Sum of the forces in the x direction is going to equal 0 because the thing's not moving, so they have to be 0. So we're just going to use the convention that forces that go to the right are positive and forces that go to the left are negative. That's kind of arbitrary. So we have FH going to the right, force horizontal going to the right, and F1 going to the left. So we'll go minus F1. All right, so we already calculated F1. So we can say force like horizontal equals F1. So then we can say the force horizontal equals 5,620 pounds. And that was one of our answers. Well, that's one of the things we wanted to find was the horizontal component of that force. Now, this is positive. We get a positive number right here, right? And how we drew FH going that way. So if we wanted the horizontal component, because it wants the horizontal component of the water on the wall. So this is, in this free body diagram, this is the wall force on the water. We want the opposite. So it's going to be the force going, it's going to be going leftward. And then because of significant figures, I put 2 significant figures, 1.0 feet, 6.0 feet. We're going to round that, and that force horizontal is going to be 5,600 pounds. So that's our answer right there. We use units throughout, and we have the correct number of sig figs. All right, so now we got to find F vertical as well. So I'm actually going to go to the next page because I have more space there. Oops. Okay, so again, we still have our free body diagram. Let's first do the sum of the forces in the vertical direction. So we have the sum of forces in the y direction equals 0. Again, nothing's moving. We're not in dynamics here. And we say that that's going to equal, we have force vertical, so that's, what happened there? Oh, I think I jumped slides. Okay, so we have force vertical, so that's down, so we'll go minus force vertical. We have weight that's down as well, so that's minus weight. And we also have F2 going up, so we'll go plus F2. So we'll simplify that to equal force vertical equals F2 minus weight. So there's our main equation, and now we need to find force 2 and the weight. So let's first do, and is it actually, I'll just pause. Anyone have any questions on that first step?
Yeah, I think I'm answering them wrong. Okay, so there's questions. Back, you had to use the centroid to find the force of the water on the water to find F1. And people are confused to why you didn't do, or did you do the 1/3 thing, or did you do the halfway thing?
So remember, in this case, we're not actually finding where that force applies. And we can't actually do the 1/3 rule because remember, we're deep in the water. So we have to do the parallel axis there, and we have to do that equation that Emma first used if we want to find the location of this force. But here we're just finding the magnitude of the force. The magnitude of the force will always be the average force times the area. The average force times the area. And to find the average force, that average force is always going to act in the middle. Well, not for a square, it's going to act in the middle. For a different shape, it'll be acting at the centroid, since the centroid of a square is always in the middle, or a rectangle is always in the middle. So if it's a different shape, it might not be in the middle, but usually it's a square or it's a rectangle. It's the force acting at the centroid, which is at the middle, which is halfway down, which in this case was 15 feet down. That's how we calculate the force. That's not where the force is exactly acting. But in this equation, when we're doing the sum of the forces in the x direction, we're not accounting for moments. We don't need to know exactly where that force is acting, just the direction of that force and its magnitude. Does that make sense? Do people still have questions about that?
So just to clarify, it's the center of the quarter circle plus the water on top of where the quarter circle starts.
Yes, it's the depth to that point, right? It's the depth to this point right here, which is first we'll go down to the top of that quarter circle, which was 12 feet. And then it's also halfway down because that's how deep it is to the centroid, which is 3 feet.
Perfect, thanks.
So you're referring to the centroid of the rectangular chunk of water, not the centroid of the quarter circle, right?
Yes, that's when I mean centroid, I mean the centroid of that square of water, right? There's this square right here. It's on this plane. Acting. So it's kind of hard because it's tilted in, but it's we have the semicircle over here. If you guys can see my hands, it's the force on this side. This is a square. So the centroid of the square is just the middle of the square. Does that make sense?
Yeah.
All right, cool. All right, you guys good? I think I'll move on. All right, so we'll go back here. All right, we'll start with force 2. So force 2, just like force 1, is going to be gamma water times HC2, which is the depth to the centroid, and then we'll have area 2. So this one will be a little bit easier, right? We have force 2, our gamma water again is obviously 62.4 pounds per feet cubed. And our HC2 is just going to be the pressure, the depth down here. This is where it's acting right here, that pressure point. So that's all the way 18 feet down. Now, in this case, since it's flat, right, it doesn't matter, right? It's going to be 18 feet. It's going to be, the depth along here is 18 feet no matter what, because it's horizontal, but obviously it changes as you go here. So we're going to say 18 feet. That's how deep it is. And the area, again, is 6 feet. It's 6 feet wide and 1 foot depth. So 6.0 feet and 1 foot depth. So again, we're going to cancel our units. We have feet, feet, feet crossed out there. If we do the math, we get force 2 equals, let me just make sure I write the right thing down here, 6,740. The only unit we have left is pounds. We know that force is in pounds, so we know we did that correctly. All right, so the only thing we're missing is that W, so we'll do it over here. So weight, as Emma said before, in her example, is gamma water times the volume of water, and we'll use that weird V with the cross through it to indicate volume. So weight equals, and I'll write again, the 62.4 pounds per cubed. So we got a quarter circle here. So we're going to do like, but it's going to be, pi r squared is the volume of a circle. But we'll do pi, we'll do 1/4 because it's a quarter of the circle. Pi r is 6, so 6.0 ft squared. And then it's 1 foot depth. So we'll go 1 foot. Because remember, it's a three-dimensional shape. It's kind of like pushes into the page. So again, cancel our units, feet, feet, feet. We're only left with pounds, and the weight is going to be 1,760 pounds. All right, we're almost done. We have to plug it into that equation. Oh, damn it. Why did I do that? Okay. Force vertical equals 6,740 pounds minus 1,760 pounds. So the force vertical is going to be 4,980 pounds. So the way we drew FV is the force of the side pushing down on the water. The question specifically asks for the vertical components of the force of the water on the 6 foot length of the curved surface. So it's going to be the opposite of that, right? 'Cause equal and opposite force. So instead of acting downwards, it's actually going to be acting upwards on that surface. So, and then also finally, we got to see our sig figs. We got 2, 2. So we're going to do force V equals, and if we round this to 2 sig figs, we'll get 5,000 pounds. We can also write that as 5.0 times 10 to the 3 pounds as well. And then remember that that force is acting vertically upwards. So, anybody have any final questions about that problem?
I have one quick question to clarify. So when you're calculating F2 and you're finding the area, what area is that?
So F2 is again, it's kind of hard because it's three-dimensional, but it's the area of the bottom. If I expand that, it's the area of the box on the bottom of this shape. So this shape is three-dimensional, right? It's
Right.
it goes back. I'm not very good.
Oh, okay. I'm with that. Thank you.
Yeah. So there's there's the box on this. Oh, this is terrible. But you see what I mean? There's a square on both the bottom and the side. And so those are those two areas that we're calculating.
Okay, thank you.
All right. Anyone else have any questions or questions in the chat, Emma?
So with that, kind of with the area she's talking about, you basically should imagine the shape that you drew for the FBD being surrounded by the tank wall, pretty much?
Yes.
So you treat the quarter circle as its own surface being acted on by the rectangular piece of water.
Yeah. So, or on the, are you talking about the bottom or the side?
Either.
So on the bottom, we treat it as if there's this rectangle interface between the wall and the water, or the bottom and the water, and it's the force of the bottom on the water. And then on the side here, it's just the force of water. This the water outside outside our shape, acting in on our shape, if that makes sense. So it's always the stuff acting in outside in onto the free body diagram.
Okay.
All right, cool. Are we good with that? All right. Now Emma's going to do another problem from the homework. Maybe not the whole thing, but just to get you guys started on it.
Yeah. You guys kind of have a pretty hard homework this time, so just going to go over it a little bit. Hopefully you can see it. Okay.
Oh, you got to share, Emma.
Yeah. I got confused. Okay. Let's take a second. Let's try and. Uh-oh. There you go. Okay, so I'm just going to go over how to help set up this problem. Just something that I think would help you guys, not related to this problem, is often to think of the horizontal force from water as a bridge. So in statics, you guys often had to solve problems like this, where you had forces coming down on a bridge, and you had to turn that into one force coming down at a certain location on that bridge. We're doing the same exact thing with these water problems. So we're turning this into just one force. I don't know. That's how I think about it. Anyways. Cool.
And just for reference, everybody, this is the first Wiley problem that's this problem, so.
Yeah. Okay, so a closed vessel of the figure below contains, and you guys can leave whenever, this will just be helpful. A closed vessel of the figure below contains water with air pressure of 10 psi at the water surface, right here. On the side of the vessel contains a spout that is closed by a 6-inch diameter circular gate. So this looks like not circular, but it is a circular flat gate stuck on the side, kind of like a teapot. Like this could be the little spout that is circular. And it is hinged right here. The horizontal axis of the hinge is located 10 feet below the water surface, right here. Determine the minimum torque that must be applied at the hinge to hold the gate shut. Neglect the weight of the gate and the friction at the hinge. So if you remember, torque is like a moment, basically. So let's make our free body diagram. So here's my gate. And here's my little hinge. Because it's not a curved surface, we're not going to need to like cut out a piece of the water. We can just look at the gate itself. So y'all want to put in the chat, if anyone's here still, I think there are, what the forces are. Might be too impatient to wait for the chat. Ooh, FB. I'm so unorganized right now. Yeah, so I guess FV for us sometimes was the force of the gate on the water, and we're not doing water right now, or we're not looking at a free body diagram of a chunk of water, we're looking at a free body diagram of the actual gate, but there will be a force from the water onto the gate, so yeah. And then I'm just gonna go, there's no weight of the gate. This hinge is gonna have forces stopping the gate from flying anywhere, so there's gonna be a hinge force in the Y, and a hinge force in the X. Oh my gosh. That's just very button. And then that is, and then there's this torque that we're looking for. Okay, so this is the weird part. There's air pressure here. You guys probably want to install this like it's a manometer, but don't do that because that would cause chaos. We're going to have this air pressure come and affect the gate. So if you think about it, if we had a tank with just atmospheric air, and then we added 10 psi, that 10 psi, that psi would be acting everywhere in this tank. Now, if we had a tank with some water in it, and so we had water pressure right here, and we had like atmospheric pressure right here, so this is what's happening, and then we put 10 psi, that 10 psi is going to be added on top of this atmospheric pressure and on top of this water pressure. It's going to go everywhere, all over this tank, which is a little weird to think about, but maybe you guys already know that. So we're actually going to have force gas right here, and it's going to act on the centroid. If we were trying to turn this force gas right here, oh, you can't see it, right here, if we were turning this pressure into a force right here, we would have it act on the centroid of this surface right here too. So we're having this act on the centroid of the gate. Okay, hopefully some people are still with me. The hard part about this problem is that you will probably need to tilt your axes to make it make more sense. So instead of having a vertical Y with gravity, it's going to be tilted because that's how your forces are acting. So while usually I would go on and start writing equations, right now I'm going to try to turn some of my dimensions into working with this new axes because it will help me later. So we know that this is 10 feet, and we know, oh, that's such a bad drawing, that this is 6 feet. I have 1 minute. This 10 feet, we actually care about this now. So what we also know about this guy is that it is a 3, 4, 5 triangle. So I can turn this 10 feet into this variable right here, which I'm going to call m, really easily. If I look at this, I have a 3, 5, 4 triangle. And basically this triangle right here is the same thing, it's just gotten bigger. So this is going to be 10 feet, and this is my variable m that I don't know. So 5 feet over 3 is going to equal the same thing as m over 10. This is some geometry. Y'all might be like, I know this. Why are you spending time doing this? So this distance, oh my gosh, my hand is so shaky, is 16.67 feet. We can also do the same thing with this distance just in case we need to know it. So it will be, what will it be? Okay, so it would be like this is m and this is 6. Okay, 5 over 3 equals 6 over m2. So m2 is going to be equal to 6 divided by 5 times 3. So this is going to be 3.60. That was just a little intro stuff. Sorry that we're over time. Okay, just to go over this real.
And just to mention to everybody, class has ended now, but so feel free to leave. You know, you don't have to be here.
Sure.
But if you want to stay to see how to do the problem, you can stay.
Yeah. Okay, so now, even though my free body diagram is super messy, we're going to look at our knowns and unknowns. We don't know this, we don't know this, so our forces from the hinge. We can solve for this, we can solve for this. And is that it? What? Oh, and we don't know our torque. Okay, once again, I do not want to solve for these forces of the hinge because that sounds like a lot of work. So I'm going to take a moment around this little dot right there that around the hinge, which I'm going to call O. So moment around O, doing my right hand rule again. This is positive, and this, okay, what will this equal? This will equal 0. Thank God. Oh, no, it won't. Maybe we won't go there yet. Okay. How are we going to do this? So we can start with T, because T, if you're doing a moment around O, T is still going to be chilling there. Oh, the 3 point. Okay, I don't know. I'm confused. I'm a little flustered. So we're going to have this, we're going to put T down. So the torque, and it's going in the negative direction. So we're going to have it negative. Then let's go, the ones we have left are FG and FW. So let's look at FG. It's going positive, so we're going to add it, and it's going to be FG times what? What in the world is it times? Well, it's going to be times this length, which is just the centroid, which we all hate that word by the end of this class, but it's going to be whatever this is. So we solve that to be 16.67 plus half of the 6 feet, which I wasn't supposed to give you guys the actual numbers, but I just will. Plus 6 over 3. That is the centroid of the gate from the perspective of our new tilted y and x axes. I should have made this call. Okay. So that was a little sneak peek into the numbers, but you guys actually don't get those. So this is going to be called LG, which hopefully you guys are paying attention and you know what that is. And then plus now our force from our water, which is also positive, which is going to be FW. And now we got to get this length, which is going to be called LW. LW is going to be a little difficult. LWD, I got it. LW will be 16.67 plus YR. Alexi, tell me if I'm doing this wrong. We switched the problem right last minute because we saw that you guys were struggling with it.
And just someone asked a question about what the that triangle is with the 3.60. That, am I right? That's just the height vertically of this horizontal gate, right? You did
yeah. So I turned this 6 feet into the 6 feet that's like diagonal into a 3.60 vertical using the 345 triangle geometry stuff. Our LW and L. Oh yeah, go for it.
So if we're taking a moment about the hinge, why are we doing the lengths like from the top of the water?
I think we're not supposed to. I think you're totally right.
It seems like we're doing
Sorry.
the top of the water.
Yeah, no, we want to do it to O. Sorry, you guys. I was supposed to do another problem right before this and change it. Okay, so with you guys as my new teacher, LG is just the centroid. Alexi, can you make sure I'm doing this right?
Yeah. So yeah, I think they're right. Yeah, this we do need to calculate that length though, right? That's the YR length that you drew.
Yeah, so isn't it just going to be that length that you were calculating, like minus the portion from the water to where the gate starts?
Yeah, you're right.
Yeah.
I think what I should be doing is I should figuring out my forces first, which might be a little less crazy. So Fg is the force from the gas. Pressure turned into force is always going to be P times area. So the P we actually were given, it's going to be this 10 psi times the area of the gate, which if you remember, it's a circle with the diameter of 6 inches. Okay, so you guys can solve for that. Force water equals, force water equals what it always equals, which is in like page 18 or 20, that one I was struggling with, of the book, which is gamma water times HC times A. Okay, gamma water we know, you guys got that. HC, it doesn't change with the axes. While Y changes with the axes, HC doesn't. So it's literally going to be this length to the centroid of this guy. Ugly, ugly drawing. Oh my gosh, come back. So I wish I had another color, but it's that. It's HC. So y'all can figure that out. It's gonna be this. Let's have this. Hopefully I'm saying this right. And then area is once again going to be the area of the gate. Okay, now hopefully I'm not leading you astray. We have this one and this one. LG, as someone so nicely saved all of you, LG is just this distance because we're doing a moment and I should know this as statics. So you're going to have to find the distance from O to the centroid, which just doesn't look like it's in the centroid, but it's literally the middle. So I guess I'll just write it. Oh, ugly. Okay, finally we have LW, which is once again this really weird thing, which is going to be, I think it's YR, Alexi, please help me. So YR is this distance. So yeah, it is YR, which if you looked in the book was IXC over YCA plus YC. So the same thing that we did in that previous problem. And you've got to pretend that you're from the perspective of water. So you're looking at the gate, you just see a circle. So this guy is going to be in your notes on that page with all the moments of inertias, and you're going to look at the one for the water. For the circle. Just losing my mind. Which I will find super fast. Okay, so IXC is going to be on page 16, and it is pi R4, R to the fourth divided by 4, the radius of that gate. Okay.
Jump in one thing. I think Emmy might have forgot the gate is 6 inches, not 6 feet, because this problem is really annoying. So that's so that 3.60 is actually, that's in inches. You're gonna have to convert that into feet. So the depth HC will be 10 feet plus 3.60 divided by 12.
That is very true. Okay. Then this is going to be that area of the gate, which you guys can all do. And this is just the centroid of the gate. So 6 divided by 12. So now we know this, we can solve for this. I messed up in solving that answer, so do you guys have questions in solving that problem?
The length of the, or like LW, the distance that we're solving for, isn't that acting at the centroid of the gate as well? Like, why are we doing the parallel axis theorem again? Is it because it's tilted?
Well, water, the location of where the force of water hits the gate doesn't act at the centroid. How you find the magnitude of the force of the water on the gate, you do need the centroid. So force of the water will probably never act at the centroid. Maybe if it's at the very, I don't know, Lexi, sometimes. But you got to use that equation from page 20 of your notes, which is YR equals YC plus I over YC A, to find where the force from the water hits the gate.
Could we use the 2/3 rule here, like in terms of just the gate, or will it change again because it's tilted?
I think it'll change because it's tilted. Is that true, Alexi?
I don't think we can't use the 2/3 rule here because it's not at the surface, right?
Yeah,
the
true.
Rule works when it's a triangle, and the force on this will be a trapezoid. So we have to use this equation at the bottom here, the like IXC divided by YC times A. So that's yeah, we can't use that shortcut. Yeah.
Yeah, so we're still figuring out office hours. Wednesday is supposed to be wellness day, but I probably will need to do them then anyways. But we can talk in the next class if you guys would rather have it on Thursday, like after 3. But yeah, I will have my office hours. I'm not sure if the professor is having his. Alexi might take over an hour of his if he can.
Yeah, so we'll announce that at the start of lecture tomorrow. We'll have that figured out.
Thanks, guys.
Thanks for being patient, everybody.
And I would say, like, this is the last thing we're gonna do with like pressure forces on a surface. So this week we'll be starting the Bernoulli equation. So if you're tired of this kind of stuff, we're almost done with it. So you can be happy about that, I guess. But this is still important to learn.
Cool.
Oh my god, that was so stressful.
Oh my gosh, I messed up so bad on the last one.